All right, so that I'm not just some talking head that you've never seen before and have no reason to trust, my name is Andrew Rademacher, as it says up on the board. I work as a software consultant here in Kansas City, and I've been programming in some form or another for about the past 10 years, or sort of close to that. But that said, I'm a relatively new member of the Haskell community myself. I've only been doing it since about September of last year. So if I say something that's wrong, or if I lie to you about what Haskell can do, please point at me, yell objection, whatever you want. And additionally, if you have any questions, feel free to ask them the moment you have them. I'm perfectly happy for this to be more of a dialogue and less of a diatribe. So there are a couple of objectives that I have today, and I want you to measure this talk by these objectives and whether or not I accomplish that for you. The first of which is that I want to demonstrate to you that Haskell has enormous potential and enormous value for real industrial applications. It's not an academic language. It's not some hole somewhere. It can give you real tangible benefits. In addition to that, I want to bust any myths, if I could speak, about Haskell being a difficult language to use. The primitives are weird. They aren't familiar, but they're not any more difficult than anything you've done in an OOP language. It's not any more difficult than figuring out how to use an abstract class or how to implement an interface or any of that nonsense. And finally, my last motive for this talk is very self-serving. My hope is that you are so enthralled by Haskell that you go out and start writing Haskell libraries so that my job gets easier. Of course, finally, I'm not going to assume that you have any prior knowledge in functional programming, but if you're coming at this with no programming experience, things are going to get a little weird. So to sort of demonstrate the value of Haskell, of course, we have to have a problem to solve. We can't really think about a programming language or what it's useful for if we don't have a challenge. And so today we're going to talk about the Fibonacci sequence. For anyone who's not familiar, the simple mathematical definition is on the bottom right. F of n equals f of n minus 1 plus f of n minus 2. So, of course, you take the last two elements, you add them together, and you tack them back onto the end of your list, and you get the Fibonacci sequence. It's a very simple mathematical principle, but it offers a lot of really interesting challenges that make it difficult to program for, or at least make it non-intuitive. Which is that first, the series is infinite, right? We can't just go calculate the series and be done with it and store it in a reference point or a library, because you would almost immediately consume all of your computer's memory, right? So we have to handle that challenge somehow. It means we have to go find a subset of the Fibonacci sequence instead of the whole thing. In addition, it's a recursive definition, right? As we can see, f of n is defined in terms of f of n, right? But we can't just say that in our program. If you actually implement directly the algorithm on the bottom, your computation time is exponential and you don't get past like the 40th or 50th Fibonacci number. Right, and finally, a challenge for most programming languages is that the values themselves grow at a very near exponential rate, which means you can't just rely on a 32-bit wide or a 64-bit wide integer and assume that things are going to go okay. That usually ends fairly terribly. But we have the nice little reprieve that we only have to deal with positive values, and if someone tries to say, I want the negative third Fibonacci number, we can just ignore them. So in order to implement the Fibonacci sequence in a traditional sort of imperative language like JavaScript, you have a very straightforward process. You define a function called getFibs, which takes one parameter, which is the number of Fibonacci numbers you want to find. Right? You then have to define an array, and you pre-populate it with a couple of literals, right? 1 and 1, which are the first two values of the Fibonacci sequence. Then you create a for loop, and you define an iterator. Naturally, you have to remember that the iterator can't be 0, because then you would overwrite your first two values. So you have to start the iterator at 2, and while that's less than the number you want to find, you increment it, and then inside the for loop, you grab the last two values, add them together. You know how this goes. Right? And this is basically how you implement most mathy kinds of things in some imperative language. Right? Of course, when you finish, you just return it up to the user. But as anyone who's worked with JavaScript, and especially anyone who's worked on V8 will know, this breaks down almost immediately. Right? Because on V8, you don't even get a 32-bit wide integer, you get a 31-bit wide integer, what they call a SMI, which is fun times for anyone who's played with it. And what that means is that you can really only calculate like the first 100 or 150 Fibonacci numbers before it turns into a double, and then, well, your last digit's not accurate, and that really sucks. So what we really need is to delve into a much more hated language, which is Java. And the reason is that Java gives us the ability to explicitly say we want to use an infinite precision integer. In Java, that's just called the big integer. But the process is effectively the same. We define an array, we give it an initial length, we pre-populate the first two values, and then we do some weird for looping. And this, we assume, makes sense. We do this all the time, but the first thing you're going to notice is that almost none of this has to do with the actual mathematical definition, right? We have to orchestrate memory by allocating an array. We have to keep track of a bunch of excess variables like your iterator I, right? There's a lot of extra work in here, but there doesn't have to be. And would you believe me if I told you that this entire function could be implemented in one line of code? Yes? No? Well, it turns out I skipped a slide. That's brilliant. Anyway, yes, the answer is yes, right? This can be implemented in one singular line of Haskell code, and I promise this is less than 80 columns. It's actually one line. But we use a lot of primitives that are weird and awkward to talk about, right? There's a lot of weird stuff in here like the cones operator, right? Conjoin. And we've never seen a zip before, or a tuple, or depending on your language, of course. But this definition meets all of the mathematical requirements for the Fibonacci sequence. We've defined in this one line of code the entirety of the Fibonacci sequence. We use a recursive definition, and Haskell's default position is to use an infinite precision integer, right? So we meet all of our mathematical requirements, but looking at it for the first time is really a what the fuck kind of moment. And it's weird to talk about, right? There is almost nothing here that's familiar with an imperative language, right? So in order to understand what's going on, we need to check out or tear apart the pieces of Haskell and talk about them individually, right? The first core principle is that Haskell is referentially transparent. No values in the entire system are mutable. And of course, the closure guys get this too, and the Erlang guys get this too, which is that a variable and a value are not even remotely close to the same thing. Right? In an imperative language, a variable is simply some little cubbyhole in memory that you go touch and mutate and do weird things with. Right? And in Haskell, a value itself, or a variable itself, is simply an unknown that you can solve with substitution. And a value itself is the mathematical definition of something that is permanent. Right? One is a value, and it will never almost be not one. Right? It will only ever be one. And so in Haskell, when you're talking about values, you are specifically talking about the thing itself and not some position in memory, which has all of the implications listed below, right? It means that values can be bound to a name just like in any other language, but you cannot assign something twice, right? And in fact, if you try and assign something twice, you get a compiler error, right? Because in Haskell, the terminology is different. It's not you have assigned something twice, it's you have defined something twice, which is completely asinine and makes no sense in a mathematical perspective. Now that informs some decisions about how the language is implemented, right? So naturally you're thinking, okay, so if we're dealing with data types like lists, how do we build those lists up? How do we build those structures up? And of course the answer is that you have to use a singly linked list. The reason being that insertion cannot occur at the end of a list, or people who have a reference to the list no longer have the same version that they started with, right? You have to always add to the front. There are some other properties that we take advantage of in Haskell. A list is homogeneous. All the types in the list have to be the same. It's, of course, immutable, but two lists can share structure. So if you insert a new element, you don't create a new full copy of the list. You, as in the bottom right figure, simply have a new element and a new entry point to an already existing list. Of course, you have all your regular basic operations. You can define lists with literals, as we see on lines 1 and 2, list A and B. And then you can perform operations on those. You just can't reassign to the same variable name, right? So we can say list C is equal to list A plus list B, which is just the concatenation operator. And it simply merges those two lists together in a new value. The value of list A and the value of list B is completely preserved, but we can now also reference and use list C. Likewise, we can do insertion operations as long as we insert to the head, right? As in line 7, where we say list D is equal to 0 conjoined with line C. And there are a couple of other functions that are not necessarily a part of the basic syntax, but we'll use to build up our Fibonacci sequence, which are the head and the tail. And for anyone who's ever played Snake on a Nokia phone, it's the same basic idea. The list has a head, which is the very first element, and a tail, which is everything that follows, right? So in Haskell, if you have a list, as in line 1, a list of 1, 2, 3, and 4, calling head on list of A will give you the integer value 1, and calling tail on list of A will give you a new list of values that was everything else, the 2, the 3, and the 4. There's, of course, a weird parenthesis thing that Haskell does, which is called a tuple, if you're unfamiliar. These are exactly like tuples in Python. These are exactly like tuples in actually a great deal of other languages, like Erlang. And they are basically small lists. The only difference is that they support proper random access, and they can be heterogeneous. And they're typically used for things like Cartesian coordinates, pairs of names, that sort of thing. They allow random access, and of course, a tuple in Haskell can be as long as you want it to be, but if you have more than 5 elements, you're probably doing it wrong. And once you have a list and a tuple, you can start doing some really cool operations with them, right? You can do a zip. And we use a zip in our Fibonacci definition, and all a zip does is it takes two lists, and it pulls them together into one list, right? So if we have an input, which is a list of characters, and another input, which is a list of integers, then we can zip across those, just like you're zipping up your jacket, and turn that into one singular list of tuples, where the input from the first position gets the first position in each tuple, and the input from the second position gets the second position in each tuple. And when the operation completes, you end up with one singular list. And it's important to keep in mind that the order of these pairings depends upon the order of inputs to your zip function. So if you have a letters list and a numbers list, and we zip those together with letters in the first input position, then the letters or the characters will get the first tuple position and the numbers will get the second. But of course, if we reverse those, then the ordering of the tuples are reversed. And if it's helpful, on line 1, you can see the Haskell type annotation for what a zip function does. It takes two list inputs, a list of type A and a list of type B, and it gives you in response a list of tuples where the first position is type A, the second position is type B. The last sort of structural element that we need to talk about in Haskell is a list comprehension. List comprehensions exist in many languages. I believe Python has one, although don't quote me on that. And I know that Erlang has one. Thank you. I appreciate that. Right? And so all we're talking about when we say a list comprehension is we have some function that we define, and we map it to every value in some input list. Right? So between the open bracket and the bar is the body of our function, 2 raised to the power of x. Between the bar and the arrow is the parameters that the function takes as an input, in our case x. And then between the arrow and the closed bracket, you have your input, in our case a list literal. So you just take the first value, plug it into x, 2 raised to the power of 1 is 2, 2 raised to the power of 1 is 2, 2 raised to the power of 2 is 4, and so on. And that's basically it. That is the entirety of the structural elements in Haskell that we use in order to produce the Fibonacci list. So if we do that, there's one problem that should be thought of, or that you might come up with fairly quickly, which is that if we define the Fibonacci list in its entirety, you get an infinite series of data, and you run out of memory. And that would be true in any language that isn't Haskell, or Miranda if you happen to have ever heard of it. If you define something in Haskell, and this is another point or part of Haskell that is very critical to understanding how it behaves, which is that Haskell's evaluation strategy is lazy. Right? Haskell desperately tries to not do work. Right? It's basically like the guy that always chills at McDonald's and doesn't have a job. In that when you define something, it doesn't actually evaluate it. It says, hey, there's an expression here, and then it moves on. Right? So you can see on line B, on line 2, we define B as being 3 plus 6. But Haskell doesn't actually know that that's 9 until line 6 of our program here. Right? On line 5, when it's printing to the console, B is actually what is referred to as a thunk. It's a real term. I don't know why. And that thunk represents the graph of the expression to be calculated. But it's not until line 6, where you print A plus B to the console, that Haskell will actually bother to go figure out what B means. Right? And this is incredibly important because it means now we can define stuff arbitrarily and assume that Haskell is not going to evaluate it. And really, that's sort of one of the fundamental underpinnings of the language, which means that now that we've talked about all the little structural pieces, we can move onward to building our Fibonacci set itself. Right? And the way we do that is we start with a list, because naturally what we're looking for is not some function that gives us a subset of the Fibonacci sequence. We're looking for the whole Fibonacci sequence. So we start with a list. And we could define it explicitly, although I personally don't have an infinite amount of time. So what we'd really like to do is define the first 2 values of the Fibonacci sequence and then have some computation that figures out the rest, right? So you can see on the second example, we split off the 1 and the 1 and the remainder of the list, right? Because we're only going to keep the first one and the second one. Once we've done that, once we've defined a list that way, we can start playing around with its values, right? So if we take on line 1 the first version of the list, and we call tail on the Fibonacci list, you can see that we have the remainder of the list minus the first element, which is interesting because it gives us a nice offset of +1, right? And if we zip the fibs list against the tail of the fibs list, then we get these really convenient pairs of n-1 and n-2. Right? The first list is an unoffsetted version of the Fibonacci sequence, and the second list is the Fibonacci sequence offset by 1. So when you zip those together, you get n minus 1, and n minus 2. Which means we can now take that as an input directly into our list comprehension. Right? So if we have fibs defined as 1 conjoined with some list, and then we define fibs2 as being taking the zip of fibs and the tail of fibs, and then simply adding those inputs together, then we get the same remainder or the same ending part of the Fibonacci sequence. You'll notice that both on line 1 and line 4, you have 2 and 2, 3 and 3, 5 and 5. And there's something I should point out. A part of the syntax that looks a little bit funny is probably why is there this tuple that exists between the bar and the arrow? And the reason for that is that the zip function produces a tuple of values, and Haskell supports pattern matching, which means we can use this tuple representation of open parand A, comma, B, close parand, to bind our A and B values in our function to the first and second position of the input tuple. So because of that pattern matching support, we don't have to have any function that sort of goes in and pulls values out of the tuple. And once we have that list comprehension, we can simply slide it up into place with the prior definition of the first two values of the Fibonacci sequence. Then we have arrived at our full definition of a Fibonacci sequence. And we've not just arrived at some program that generates a subset. We've not arrived at a series of instructions that tells a computer how to build it. What we've arrived at is the full definition of the Fibonacci sequence in kind. Right? The Fibonacci sequence is an infinite series. What we've defined here is a recursive infinite series. The Fibonacci sequence is self-referencing. What we defined here is fibs defined in terms of fibs, so we have our self-referencing requirement. And because Haskell's default integer position is to be infinite precision, we can also handle the exponentially growing values of the Fibonacci sequence. And finally, because it's a list, Haskell will just give you an out-of-bounds exception if you try and go to the negative third index. So we've met all of our mathematical requirements for the Fibonacci sequence, but of course, the first notion that you get whenever you deal with languages that are very expressive is that they have to be slow, right? I mean, we're familiar with this. We're always taught about this. Languages like Ruby and Python are really great because they're expressive, but for some reason, they're also insanely slow. And this turns out to not be the case with Haskell at all, right? If we compare the two Fibonacci versions, the Java version on the left and the Haskell version on the right, you can see that the implementation of the Java version is 8 lines, and the implementation of the Haskell version is 1 line, one singular line. And of course, you have to have a main function to deal with input somehow. So if we open up VTOP and look at our CPU utilization and our memory consumption, and actually put this whole notion that expressivity means slowness to the test, compile our Java program, and then run it. And of course, we're going to be computing a lot, so we have to play around with the VM a little. You'll notice that our memory consumption flies through the roof. Occasionally, you get a GC pause on the VM, which is the spike of 100% CPU utilization. And the computation can be performed in 8.6 seconds or so. Right? So this is the 475,000 Fibonacci number, found in approximately 8.6 seconds. And that's the Java version. And then, of course, Haskell compiles to full native, so we do a build, and for some reason, something is using a lot of my processor. Right. And then we run the application. You can see a constant level of 14% CPU utilization, no memory consumption, and our computation was performed in 6.3 seconds, right? Which means we have a 30% performance gain over Java. Now, Java is not by any means a slow platform. Java can usually be fairly comparable to C. It's a robust system, and as much as you might hate the language, the VM is great. And yet Haskell is still able to produce a much faster result to the same place. And there's an interesting thing that happened. You notice that when we did the Java application, our memory consumption spiked up to almost 100% of the computer. But you notice that our memory consumption here flatlined. And in fact, if I look at the debugging output, you'll notice here on line 6 that our total high watermark for memory consumption was 96 megabytes. And the reason for that is that because Haskell maintains a linked list as its internal list representation, the compiler knew that we were only using the list once, and it was able to let the garbage collector reclaim the first and early values of the Fibonacci sequence while we were computing values of the Fibonacci sequence. It didn't have to keep all of that data in memory. And so you get all of this wonderful expressivity with really what is performance comparable to C, that fun world. But the expressivity doesn't really stop there, right? Because Haskell itself cannot just be run in a compiled mode, but also an interpreted mode. So we can load it up into a REPL as if you were in Clojure or some other language. And then we can start operating on our Fibonacci sequence, right? We can say, and I'll turn on the timer here. We can say, I want the 300th Fibonacci number, or I can have a problem because this is a live demo. So I can say I want the 300th Fibonacci number and get the 300th Fibonacci number. But this is a functional language, so now that we've defined a list, we can use all of our regular list operations on the Fibonacci sequence. I can say maybe I want to take the first 10 Fibonacci numbers, take the first 100, 1,000, we'll do 1,000 Fibonacci numbers, or take the sum of the first 1,000 Fibonacci numbers. And all of that can be done in the full functional style without any recompilation and on the fly. And another interesting caveat about how this thing works is that because Haskell can know that your values never change, Haskell can intelligently memoize values. So if we're in the REPL and we say, I want to find the 475,000th Fibonacci number, and of course that will take some time, but you'll notice that our memory consumption is climbing. And the reason for that is that because Haskell can't prove that we don't need these values again, it goes ahead and memoizes the entire list. So once I've generated my values, I can then recall those values. You'll notice that to find the I believe we did, 475,000th Fibonacci number, it took 7.10 seconds, or 7.10 seconds. But if I recall that number again, it's just the time to traverse the list and then display the number. And interestingly, where it gets really fun, is that I can now start adding values and computing further and further values down the list as fast as a quarter second, right? Because it just has to retraverse and redisplay. Right? And the reason for that is that Haskell can intelligently memoize the independent values in the list without having to actually copy data from an array to an array and without having to recalculate. Right? So you get all of these wonderful advantages without having to give up performance, without having to give up expressivity. You get C performance, you get expressivity that's better than Ruby, better than Python, what have you. Right? So that is fundamentally the case that I'll make for Haskell today. If you want to get the code for this talk, you can grab it from GitHub, or you can contact me at Twitter or LinkedIn or what have you. So that's pretty much all I have to demonstrate. So if there are any questions, go for it.
I'm just curious what kind of community is around Haskell. If you're using Python, there's all kinds of awesome standard libraries and additional libraries. How does that compare with Haskell?
So the community for Haskell is absolutely smaller than Python. Python's one of the largest around, but it's very, very active. There are 4 major web development frameworks for Haskell. There are white papers written for Haskell all the time. GHC itself is under constant development. So the community itself is very active, and to give you a perspective of scale, pip has approximately 49,000 packages on it, which is the Python package index, and Hackage has about 5,000 to 6,000 packages on it, so for a point of comparison in scale.
Great, thanks.
Unless you all go start writing packages for Haskell, and then that number goes up, and that's good times.
A great presentation. That's very interesting. Can you just, I might have missed it at the beginning, but did you say you use this in your professional work, or is this just something?
Absolutely.
So can you describe how you use it professionally, like what problems you are solving with this language, and then maybe contrast that with you moved away from Java to this and what improvements you might have experienced?
Right. Yeah. So I did Node for a long time. I did a lot of Node apps, and I built on the Node platform. And naturally, like everyone, I get tired of callbacks. And so when I started to really get a hold of Haskell as a language, I started using it for client work. And I'm now using Haskell with one of 2 web frameworks, either Yesod or Scotty, to actually build web applications just as you would build in Node, but with Haskell. And of course, the advantages that you get for that is that Haskell as a language compiles to a native binary and gets native level performance, right? So you no longer have to deal with callbacks. You no longer have to deal with typing problems that come from not having type annotation, right? It's a static language. And interestingly enough, the Warp web server, which is what Yesod and Scotty are built on top of, is now faster than Nginx. So it's a more capable system overall. It's capable of handling more concurrent connections. And as a result of that, my clients save money because it takes less servers to run their stuff. Okay. Well, I appreciate your time, and I hope you guys enjoy the rest of the conference.